So hello everyone, welcome to the next joint meeting of quantum computing groups from Washington, Warsaw and Toronto. Today we have a pleasure to host a great speaker, Dr. Kipper Sharkey. So Kipper, welcome. It's our honor to have you with us and thanks for accepting our invitation. So Kipper will give a talk titled A Deep Dive into the Future Quantum Computing and Hardware from a Chemical Physics Perspective. So this meetup will be moderated by me. So my name is Paweł Gora, and the second moderator is Sebastian Zając. We are both from Q Poland. So Q Poland is also one of the organizers of this meetup. And before we start, we would also like to tell you about our plans for the next two meetups. So the next one will be in January, so next year on 8th of January. The title is Creating Quantum Circuits for Hundreds or Thousands of Qubits. The speaker will be Yuval Boger. And later in January, there will be another talk titled Genetic Optimization Acceleration Using a Quantum Annealer. So this time, the speaker will be Vinay Fadnis. And also, we would like to thank our sponsors, partners, so Quantum AI Foundation, which is a charity organization supporting education, research, and collaboration in new technologies like quantum computing. So I'm personally a CEO of this non-profit organization, and also we organize meetings of the Warsaw Quantum Computing Group. So the next one will be on Monday, by the way. Also, I would like to thank the Quantum Computing and Data Science Group from Toronto and Zen for Quantum and Orion XNet. Another partner would like to thank Association Quantum and Cambridge Quantum. And as I said, together with Sebastian, we are also representative of Q Poland. Right, so I think that we can start. So I would now stop sharing my slides. Maybe one more thing that is important. So this meeting is recorded. So as usually, the video will be later available on our YouTube channel. And if you have any questions during the lecture that will be given by Kipper, please post your questions on our chat. So we'll try to ask your questions during the lecture. So Kipper also prefers this meeting to be more interactive, but there will be also a Q&A session at the end. And I think that's all. So I'll now stop sharing my slides, and Kipper, if you're ready, the Zoom is yours, so you can start sharing your screen.
Well, thank you very much. I want to say thank you to Helen specifically for inviting me to give a presentation. We've been going back and forth a couple times over the last year or so on, what to present and what would be appropriate for this group. And I also want to thank the moderators today for joining us from Poland. The title of my talk is Why Pauli Exclusion Principle Applies to Bosons. And I'm not sure if my Zoom is covering this up. It's a deep dive into the future of quantum computing and hardware from a chemical physics perspective. I gained inspiration for this talk a few meetups ago. Back in September, there was a meetup and there was a discussion going on about the Pauli Exclusion Principle. And I wanted to clear up some misconceptions about that and bring to light some new developments that have been happening with the Pauli Exclusion Principle and how it applies to chemical physics and possibly even qubits. So let me go to my next slide. So just some background on myself. I have a bachelor's in chemistry and mathematics from the University of Arizona in 2010. And I also received a PhD in chemical physics, also from the University of Arizona in 2015. My current citation level as of 2 days ago is 398, and I have about 29 papers published. My PhD advisor, Ludwik Adamovich, is actually from Warsaw, Poland, and that's where he got his degree. And we currently have some collaborators that are also in Poland. Her name's Monica, and she's at Nicholas Copernicus University. So I just wanted to mention that. So the next slide. According to Quantum-Appaloosa website, the talk today is for the quantum ready, so 400 level. So there's certain aspects about quantum and computing that I'm not going to review. So I expect that most people on the call today know what a wave function is, what a qubit is, how that's defined. And so I'm not really going to go into too much detail about those kinds of things. But we are going to take a deep dive into those concepts. Okay, and then I'd also like to ask specifically to the audience, is there anybody in the audience who actually uses the Pauli exclusion principle in their work, physicists or chemists alike? And feel free to go on mute and introduce yourself. And if not, then that's okay too. Any takers? Anybody in the chat?
Oh, as for now, one person replied that no, so I guess that.
Okay. Very good.
Yeah. Okay.
Okay. Great. All right. So the goals today of this talk are to raise awarenesses between the differences of the Pauli exclusion principle, the original one, and the generalized Pauli exclusion principle. Okay. And what was formulated nearly 100 years ago versus how we can implement this in today's technology. Okay. I'm also going to talk about explaining wave functions that include the generalized Pauli exclusion principle. And we're going to discuss symmetry and anti-symmetry dependence of these operations. And we're going to go over some examples from chemistry and some gate operations. Okay. So Pauli said, the best that most of us can hope to achieve in physics is simply to misunderstand at a deeper level. So for a long time, his principle only applied to fermions. And it wasn't until we started developing physics and uncovering new kinds of particles that we realized that the Pauli exclusion principle could be extended to bosons. And so some history I'm going to go over. So it started out in 1924, really with Born-Oppenheimer and the Born-Oppenheimer approximation that basically neglected the motions of nuclei. We call this an infinite mass approximation, and only considered the motions of electrons. And so when Pauli was thinking about what he was thinking about when it regarded the symmetry of electrons a year later, he didn't really think about bosons. He wasn't really concerned about that. He was concerned about electrons. And about 10 years later, James Chadwick announced that the core of atoms also contained a new particle called the neutron. And so they were still really learning about even how nuclei were composed. So they didn't really know back when they were formulating the Pauli exclusion principle. And then years later, we finally discovered the Higgs boson. Okay, and this is part of the standard model, and it's still being worked out today. For instance, we don't know if there's a spin 1/2 graviton, and can we discover it? And could this lead to space travel and aliens and all sorts of other, exotic ideas? But really, what I wanted to talk about today is how that his principle 100 years ago is now being extended to new kinds of particles that we have discovered based on the fact that we have better measurement techniques and computing, so back when Pauli was working on this, we didn't really have a high level of computers like we do today. So our computing power has gotten better over the years. Okay. And Pauli received a Nobel Prize. He was nominated by Einstein. And part of what he was saying when he gave his talk in 1946, actually on December 13th, 5 days ago was his anniversary for receiving the Nobel lecture. He said that there is either a mixture of all symmetry classes, which he says that it's probably never realized in nature, okay? And the second case is that there's only symmetrical classes, all right? And then also only anti-symmetrical classes. And he said that it is this possibility which actually holds true for electrons. So he was specifically saying that electrons have an anti-symmetry, okay? And he wasn't sure about the rest of it. So the original Pauli exclusion principle applies to particles that have a half integer spin, okay, and are described by anti-symmetric wave functions. So in other words, when we permute two particles of a total wave function, we need to get a minus sign out of that total wave function. It has to be anti-symmetric, okay? Aij is an anti-symmetric operator that acts on pair particle indices, okay? And the total wave function is a function of all particles. The generalization of the Pauli exclusion principle, yes?
What is there a difference between anti-symmetry and broken symmetry?
And broken symmetry.
Yes.
Well, that also leads to asymmetry, and so asymmetry is different than anti-symmetry. Anti-symmetry is very specific to having this reflection of minus sign on the total wave function. So broken symmetry doesn't have that particular characteristic.
Thank you. Now about the permutations.
Mhm.
If you do two permutations, you stay in the same sign, the minus sign disappears.
So the wave function has to be anti-symmetric with respect to pair particle indices. And I'm going to get into this operation, but it has to hold true for all permutations of identical particles, very specifically of identical particles. And this becomes very complex as the wave function grows. So it's actually an NP hard kind of calculation. So it scales factorially with the number of particles as it grows. So, and the same holds true for symmetric wave functions. So we have a symmetric operator that operates on a total wave function that comes with a plus sign, okay? And this is for bosons, so integer spin particles, okay? Now, we have to understand what kinds of particles actually we can apply this to, right? So there are elementary particles, which are, let's see, go back. We have elementary particles that are photons and which we don't consider in chemistry. And we have nuclei, right? So nuclei are actually composite particles. And we're able to generalize this Pauli exclusion principle to a very generic form where we actually have a -1 to the power of 2 times the spin acting on a wave function. So this can be completely generalized in this way. Okay. Now it gets, as I said, it grows in factorially. So at some point we have to understand how does this apply to canonical ensembles. And there's a recent 2020 paper that talks about this. And I highly recommend reading this source. It's open source, so anybody can take a look at it. And it's titled The Theory of Non-Interacting Fermions and Bosons in the Canonical Ensemble. And they very specifically use the definition of the generalized Pauli exclusion principle, but they don't talk about that. They don't mention that, okay? In summary, they say within the unified framework of auxiliary partition functions, so we're going to talk a lot about partition functions today, it is straightforward to obtain most of the well-known general relations in the fermionic and bosonic canonical ensemble that were previously derived using a host of different methods. So there are many physicists and chemists that may or may not use the Pauli exclusion principle. And if they do use it, they may not actually refer to it as the Pauli exclusion principle. So we need to start coming together as a community and understanding when is it being used and how is it being used and how can we leverage this in computations and chemical simulations. Okay. So as I was saying, fermions and bosons, we have subatomic particles, which are the electron, proton, and neutron, and they all have a spin of 1/2. They combine together to make nucleons, and these nucleons can be, at least protons and neutrons, these nucleons can be bosons or fermions, depending on how the spin adds together. Okay, and like I was saying, that the photon of light has a spin of 1, and we don't really care about that in chemistry for the most part, unless it's actually interacting with the chemical substance. So in general, we say that spin can be paired, anti-parallel, or spin unpaired, which is parallel. And we usually denote this with arrows, up or down. And so if it's spin paired, it'll be an up and down arrow or down up. And parallel spin will be up, up, or down, down. And some examples of composite particles, we have composite fermions, which is the deuterium isotope of hydrogen, which has 1 proton, 1 neutron, and an electron, spin of 3 halves, and the spin multiplicity is 4. So I'm going to go over spin multiplicity and how we create wave functions based off of the multiplicity. Okay, so nitrogen atom has 7 electrons. The spin of those 7 electrons is also 3 halves. Lithium, the nucleus of lithium is a fermion. It has 3 protons and 2 neutrons. Okay, so now we go into bosonic particles. We have hydrogen molecule, which is a bosonic type particle with 1 proton and an electron, spin of 1. Neutron, or sorry, the deuteron, the nucleus of hydrogen with an extra neutron also has a spin of 1. Okay, and there's some other elements that I've listed here. This is not an inclusive list, obviously, just some examples of how you can obtain composite bosons and composite fermions out of fermionic particles. So going on to spin, when we have a spin of 0, that forms a singlet spin function, and a singlet spin function is antisymmetric spin pairing, which means we have a minus sign when we permute 2 of the particles. Okay, so we have spin up minus spin up, spin down minus spin down, spin up. And that's the spin function. But the spatial wave function that comes with this is symmetric. So the product of an antisymmetric wave function times a symmetric wave function is always going to be antisymmetric. Okay, so it preserves the symmetry. Then we have a doublet state. That doublet state can have any number of paired electrons, but at least 1 is up or down. Okay, and this leads to a combination of function for spatial and spin. Okay, so we don't know how the spin pairing works out for all of those other electrons that might be there, or protons or neutrons. Okay, the triplet state has a spin of 1, and it's a multiplicity of 3, which is a triplet state, which means we can have spin up, up, or spin down, down. And then the spin paired state where we have a plus sign. So it's a symmetric spin pairing. So it's different than the antisymmetric spin pairing of the singlet state. Okay, but because of the symmetry of the spin state, the spatial function has to be antisymmetric with respect to exchange. And this antisymmetry of the spatial wave function has to be obtained by doing the permutations, and we have to be able to understand how to come up with those operators. Quartet state is very simple, similar to the doublet state, where we have 3 spin ups or 3 spin downs, and again that comes yields a combination spatial wave function. And when we have more than 2 or 3 particles, the wave function, the total wave function, can actually become very complicated and entangled, as we call it, which means we can't separate the variables as a product. Okay, so in general, when you're talking about 2 to 3 electrons or 2 to 3 particles, the wave function is generally non-entangled, and you can separate the variables. Okay. So in general,
clarification, please. The spin function is a component of the total wave function. How they relate?
The total wave function in general is a product of spin and spatial functions. And I have a slide on that, so I'll get to that in a moment. But in general, it's a product of spin and spatial functions. Now, especially in the one particle case, that's true. The two particle case, that's generally true as well. But as you have more and more particles, the entanglement, so the ability to unseparate the spin and spatial parts, become more difficult, and it becomes increasingly harder to write a wave function for entangled particles out of spin and spatial components.
Thanks.
So here on this slide, I have how we couple together the spin of two particles to obtain an antisymmetric wave function. So the spin out of 1/2 particles coupled to a 0 state, so spin 0, 0, is done by where we have spin up and spin down minus spin down plus spin up, and we get a 1 over square root of 2 in front of this. So this is how we do this coupling in terms of the math. All right, now really quick, we can talk about a qubit. So addition of momentum and Klopsch-Gordon coefficients deriving the state of a qubit. All right, so with a qubit, we actually use orbital angular momentum instead of spin, and spin, we use both. So the first column, if we're here in this light yellow box, we have a total Klopsch-Gordon spin of 1/2 coupled to 1/2, where we use angular momentum value equal to 1. And when we go through this coupling, we actually end up getting the result of, seen in the darker yellow over here, where we have cosine of spin up plus e to the minus I theta spin sine theta spin down. And this comes out of spherical harmonic functions. And in general, for the state of a qubit, we use a phase shift and phase theta by 1/2. Okay, and that's seen down here. And we can actually go to the Grok block, which I'll open up in a little bit. I'm going to switch screens and explain to you how the Grok block, how we can actually see these states in angular momentum with spin equals 1 and 0. So I'm going to come back to that idea in a little bit. All right, so the total wave function for chemical systems is a product in general, or not a product, it could be entangled. It's a function of spatial R and spin variables, and generally time, although we don't have to consider time if we're looking at static states. And R is a vector of small r's, so basically every single particle has some kind of position in space in spin functions, okay? And in general, we use a Cartesian coordinate system for this, x, y, and z. And spin can also have x, y, and z spatial coordinates as well. And in chemistry, we don't reduce R to equal 1. So R can be as long a vector as we want it to be, okay? But the state of a qubit has set R equal to 1. So the differences between a qubit and chemical particles is that R can be greater than 1 or less than 1. So the coordinate system is the same for a qubit and particles in chemical analysis. So the wave function can either be entangled, like the Bell states. So I'm sure most of you are familiar with the Bell states. Each component of the Bell state can only be measured with the probability of 1/2, either the 0, 0, the 1, 1, or the 0, 1, or the 1, 0 state. Okay, and so they're entangled. But separable degrees of freedom come down to the Born-Oppenheimer approximation. So as I was saying, the total wave function can be separated into products of functions. And this comes down to understanding that nuclei have a particular set of functions, rotational and vibrational, And electronic functions sort of follow what the nuclei are doing. So Born-Oppenheimer said that we can treat nuclei separately, and the electronic function can either be separable, okay, so a product of spin and spatial, or it can also be entangled. And really this comes down to what level of theory you're using and how many particles you actually have, and are they entangled or not entangled. All right, so this leads me to other concepts of the total wave function, like superposition, where you have a linear combination of basis functions that have a linear coefficient. And then we include symmetry. So y operator acting on a wave function ensures that we have the total symmetry operation that we need in the wave function. And the wave function is, again, spatial and spin coordinates in the superposition. And y is generally a product of symmetry, symmetrizer, and anti-symmetrizer, okay? So that when we get ready to go calculate calculate energies or expectation values, all right, we need to understand y dagger and y together, multiplied together. So y dagger y is actually equal to an anti-symmetrizer times the symmetrizer times the anti-symmetrizer. And this is because spin is actually idempotent, or sorry, not spin, but the symmetrizer is idempotent. So when you take the symmetrizer dagger, so the complex conjugate transpose times the symmetrizer, you get the symmetrizer back. So we're able to reduce y dagger y to be a dagger SA. And when we calculate the expectation value using the variational theorem, we have all of the spin functions, all of the spatial functions, the Hamiltonian operator, and y dagger y. And we're applying the superposition principle in this formulation. Okay. So what is the symmetrizer and anti-symmetrizer? Well, it's a product sum over these pair particle permutations that come from a particular setup. So we have to understand the system that we're looking at. And of course, there's going to be some sort of expansion coefficient that comes with doing this pair particle operations. And these expansion coefficients are determined by understanding how the Young operator is built, okay? And there's going to be certain coefficients that come with these operations. And in general, these operations are determined by building Young frames. So when we have two particles that are fermions, we usually build a column, and we fill in the columns with 1s and 2s, or whatever particle label it is that we're looking at. And for bosons, we have a row. So we fill in across the rows. And symmetrizing comes from permuting particles across the row, and anti-symmetry comes from permuting particles down a column. So as we build identical particles, in the fermionic case, we're going to have one long column. And for bosons, we're going to have one long row. But in the composite systems, we have to understand what kinds of particles are being paired and what kinds of particles are being symmetrized and anti-symmetrized. So when we have 3 particles, we can have 2 being spin paired in bosonic case, and 2 of those can actually be anti-symmetrized. So symmetrizer and anti-symmetrizer, which is where these colors come from. And in the n equals 4 case, we have a very unique situation where we can have the top 2 rows, the top row be symmetrized, the bottom row be symmetrized, and the columns also be anti-symmetrized. And so this gets very complicated very fast. And so what I'm going to do now is show you the actual operation for this. Okay. So we're going to look at this 4 particle situation for bosons first. Like I said, this is an n factorial operation. So we have 4 factorial, so there's 24 terms here. And the symmetrizer is built by first taking identity and adding it to the permutation of particle 1 and 2. And then we multiply that by another operation where we have identity plus the permutation of particle 1 and 3 plus the permutation of particles 2 and 3. And then we also multiply that where we have identity plus the permutation of 1 and 4 plus the permutation of 2 and 4 plus the permutation of 3 and 4. And when you expand the symmetrizer, you get all 24 terms that give you a unique particle set. Okay, so it gives you all the operations that you need. And because it's symmetric, they all come with a plus sign. And in this particular case, the coefficient happens to be 1. So plus 1 on all permutations. Okay. But this can get very complicated very fast. So in other words, when you have the anti-symmetrizer for fermions, okay, this symmetrizer is equal to 1, but the anti-symmetrizer becomes basically the same operation as the symmetrizer in the previous example, but with all minus signs. Okay, and so you permute, you go through the permutation, and when you take y dagger y, you actually yield 576 terms that need to be reduced down to 24 terms and determining the coefficients and plus and minus signs. And you can imagine as this mixes together, it's also going to mix these minus signs. Some operations will become positive, some will stay negative. And the answer to this question will be revealed at midnight on my website on January, basically December 31st, GMT time. Okay. And I encourage the audience as a little test to see if you can come up with this operation on your own using Python. Okay, see if you can. And if anybody has the answer, you can go ahead and please share it with me and we'll see if you're right. And the same thing holds true with these other cases. So this becomes quite complicated for when you have 2 particles that are symmetric and 3 particles that are anti-symmetric. The combination of y dagger y becomes quite complicated. Okay, so again, the answer will be revealed at midnight on New Year's. Okay. And again, the same situation over here where you have 3 particles that are symmetrized and 2 that are anti-symmetrized. Okay, I have the full operator listed here, and so you can go ahead and try to come up with what that operation actually looks like. Okay. And again, same with the other 4 particle case where you have 4 symmetrized in total, but in this very particular Young frame. Okay. So the chemical examples that we're going to talk about today are H2, the hydrogen molecule, and D2, where we have an isotope of hydrogen molecule made out of deuterium nuclei. Okay, so we're going to first talk about the ground state, and then we're going to talk about excited states. So the ground state of both molecules actually happens to be a singlet nuclear state. So the protons of H2 have an antisymmetric spin function, as well as the deuterium nuclei of deuterium. They both have antisymmetric spin function. So their spatial function is actually symmetric. So the total wave function actually has a parity of +1 because of the symmetric wave function. And so we go through this symmetrizer, and so we symmetrize the nuclei here, and the spatial wave functions of the nuclei and the spatial wave functions of the electrons, because the electrons are also in a singlet spin state. In the variational theorem, we can actually integrate over spin first, because we're using normalized spin functions. And when we integrate over spin, it equals 1. And so we actually don't have to really represent the wave function in this calculation. So the wave function actually becomes only spatial part. So we call this spin independent variation. Okay. So we're going to use the variational principle again, but only using this spatial parameters because we've integrated, so-called integrated over the normalized spin functions. And when we do this, we have to include all of the permutations. So we're using an explicitly correlated method in this particular approach where we have a Gaussian function that has an A matrix that contains all of the information on the particles that we have, plus we have to permute the A matrix according to our permutational operators. So we permute the 2 electrons, we permute the 2 protons or the nuclei, and then we have a combination where we permute both the protons and electrons at the same time, okay? The AK matrix that we use in the basis functions for these calculations is built out of a Haleski factorization that is a Kronecker product with identity matrix in the 3rd dimension for X, Y, and Z. So they're spherically symmetric functions. Okay, and when we go through this calculation and we produce the wave function, we can actually yield a plot that's spherically symmetric. So this is what the wave function in a high vibrational state looks like for parahydrogen, okay, with an anti-symmetric spin function, okay. And we calculate many different vibrations. So this particular vibration happens to be, I have to count the nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the 11th vibrational state. So when we look at excited H2 and D2, we're actually looking at an excited spin function, which is the triplet function, and that's symmetric. So now we have a spatial function that's anti-symmetric. So we have to do something to the wave function that was previously totally symmetric to get an anti-symmetric wave function. To do that, we multiply the wave function by Z. Now, many of you might recognize this operation as the Pauli Z operation, okay? So when we multiply the wave function by Z, we get this sort of polarized spatial properties. So now we have, you can see the lobes. You can actually compare this to in chemistry where we have a P function. Okay, so this is an excited state P function. It's the lobe or the dumbbell shape that most people are familiar with looking at. So this is actually can be represented in a qubit as well. So as soon as I pull up that website to show you, we're going to come back to this idea. Okay. Any questions about what I'm showing here?
Well, there is some observation that the picture you showed maybe 2 slides ago, okay, this one reminds me a splash and ripple effects when I throw a stone to a lake. And then in your current slide, this, if you can go, yeah, on the right side, it looks like this ripple pattern is now warped and distorted. And maybe you can make a comment how that shape is being generated or.
So yeah, so there's a ripple shape. This has to do with the vibrations of the molecule. Okay, so these nuclear vibrations. So even though it's in a ground state, ground spin state, so spin equals 0, we can vibrationally excite these. Okay, and those vibrational excitations are either going to be symmetric or anti-symmetric. And so this anti-symmetry also vibrates. Okay, so it also has this ripple effect as you go higher and higher in the vibration, but it still is going to preserve the symmetry of that vibration. So you can see that the vibration parts that are way out towards the end still have that kind of same shape, where we have the single, this is the first vibrational state that's on the left hand. So as it gets higher and higher vibrated, that symmetry is preserved, but it's going to have that ripple effect in space. And so back to how it was generated by solving the energy in the variational theme. So this is a variational optimization energy calculation, and we were able to produce these plots.
Can I ask something too? So your
Oh, you went back on mute.
oh, sorry. Can I ask something about the state space? It's not only electronic state space, right? It's also a nucleus state space there.
Yes, it's
combined.
It's combined. It contains information on both the nuclei and the electrons. That's correct.
And you mix all the spins with this
Yes.
mixing.
Yes. Yeah. So in this particular example, we keep the electrons in the ground state, and we don't excite the electrons. We only excite the nuclei.
Nice, thank you.
This is deuterium, right?
This is actually H2. This is H2.
Right.
I'm going to show deuterium. I'm going to show some numbers for deuterium in the next couple of slides. Okay.
I think if you had some labels on those colors, that will probably make it sort of explicit, but I like the explanation. Thank you.
Okay, so the colors actually just correspond with the values on the axes. And so we're just trying to show that that where the line is for the values on the I guess would be on the y-axis going up, because we have x-axis and z-axis on the bottom, and y is going up. And the colors just indicate the various levels that we're at on the y-axis. So how polarized it is.
So one more question, really quick, because I have some fortunate to leave in a few minutes. Could this method also be applied to anions?
I'm sorry, to what?
To anions, not bosons, neither fermions.
Yes, yes. So you're talking about like a neutron. Yes, yes. Okay, so as I was saying about the Born-Oppenheimer approximation, in this particular method, we were not using the Born-Oppenheimer approximation. And when we do this, we solve this variationally. We're actually lower in energy than calculations that use the Born-Oppenheimer approximation. And in general, we're lower everywhere. The ground state, there really is no difference. So the Born-Oppenheimer approximation doesn't really make a difference in the lowest vibrational state. It's basically a zero difference. But as we excite a molecule to a higher and higher state, so the 15th state, we actually get a very, 10%, a little more than 10% difference between the Born-Oppenheimer approximation and the non-Born-Oppenheimer approximation. And this really comes down to the reflection of being able to consider the nuclei in the wave function, and also consider the symmetry and including the Pauli Exclusion Principle. Okay, so this was generated for ortho-para-spin isomerization. And our Born-Oppenheimer difference is green, and the Born-Oppenheimer calculation is in blue in the top plot. Okay. So here are some numbers for ortho-para-spin isomerization of D2, so deuterium. The first column is non-Born-Oppenheimer, so not as so basically having this correlated basis function with the nuclei and electrons alike. The second column has to do with the Born-Oppenheimer approximation, And we have the difference basically in wave numbers, and then we compare it to actual experiment. So what happens on the lab bench? So we have two computer simulations and compared to an experiment. And basically with deuterium, we come in slightly lower in energy than the Born-Oppenheimer approximation using the same methodologies. Okay.
One more
And-
question, sorry. Can you get also Raman frequencies from this method?
Yes, you can. Yep, you can get those kinds of frequencies. Mhm.
Thank
All
you.
right, yes. So the next slide. Fermion to qubit mapping. Right now, the current level of theory for the qubits is only extended to mapping to fermions and specifically electrons and molecules. Okay, and they go through some very complicated mathematics with spin orbits, and I have the reference down here at the bottom. This was done, I think, January of 2017. But what they're not considering are nuclear configurations. Okay, so what's happening to the nuclei in these calculations? They're only considering the spin orbits of electrons. And so, you know, what about bosons? How do we map bosons to the qubits? Those are all very active and open conversations that we should be having in the industry. And I'm hoping that this talk today can get us to a place where we can start to understand the symmetry of bosons versus the symmetry of fermions, what's happening with a qubit, all right? And there's been some recent news where now we're not just considering qubits, but we're considering qubits, right? So Rigetti announced that we have a three-particle or a three-state system now with a square root of 1/3 instead of a square root of 1/2. And can that lead to any extra flexibility to where we can start accounting for nuclear effects in these calculations as well? We can also extend this idea to qubits, right? So multi-dimensional, so not just two-level systems or three-level systems, but multi-level systems, okay? And the simulation method that we have for understanding chemistry can actually help us potentially design these qubits, okay? So that's the hope, is that through using the extended Pauli exclusion principle, generalized to different kinds of molecules, we might be able to come up with very flexible hardware and very flexible modeling that we can use in computing. Okay. So I have a list of references here so that everybody can go through and take a look at. And with that, I can take some more questions or go back and talk about certain ideas.
Okay. Thank you, Peter. There is one question on our chat now. What's the actual feasibility of qubits based on chemical molecules?
The actual feasibility.
Yes.
Well, right now we're looking at very small systems. So let me go back to this. These are, you know, a few electrons, you know, 14 to 16 to 20. Okay, very small electrical spaces and not very many nuclei. Now, I should say that quantum computing is also being used for general optimization problems. And so we're using this for large molecules like DNA or other things like that. But that's a very different problem than looking at very specific wave functions for very specific chemical problems. Okay, so there's different kinds of methodologies that are being used out there for quantum computing. And I don't know all of the details because I don't actually use this particular methodology right now. The calculations, I should say that the calculations I do, and producing these plots have all been done with classical computing.
Okay. All right. Are there any more questions? So there was a question earlier about the paper. So we can go back.
Mhm. This one?
Let
This
me
one?
just check it. Yeah, there was a question from George. Could you give a link to this recent paper with regards to canonical ensemble?
Oh,
And
yes, yes. Absolutely.
Alan replied, I'm not sure if that's the correct paper. The title is Theory of Non-Interactive Fermions and Bosons in the Canonical Ensemble.
Mhm. Yes, that's the correct paper. And
Oh,
it's,
okay. So Alan, thanks for this. Okay.
I'll go back. Let's see.
All right. Do we have any more questions?
Yeah,
here?
there is a very naive question. At the very beginning, you showed the block sphere with radius 1, and on the right side, there was comparison to R, and R can be larger than 1, and this is the relevant for chemistry.
Yes, yes,
Can
that's
I learn
correct.
from that? Can I learn from that that possibly on your analog to block sphere with R bigger than 1 allows more degrees of freedom that chemistry requires?
Yes. Yes. So basically, we actually don't care about what R actually is because we integrate over all of space. But we're saying that it can be anything.
So
Okay,
it is
so-
anything because we need more complication or more sophistication in chemistry, right? More possibilities.
That's correct. Yep. And we don't know how far out in space that R vector is going, you know, and that goes back to the diagrams, essentially where you might have vibration or rotation, and that wave function might grow in space, right? And so, but in the variational theorem, so let me go back to the variational theorem right here, we integrate over all variables. We integrate over space. So at the end of the day, when we do the mathematics, we don't actually care about what R looks like in that integration.
Now, the Pauli exclusion principle intuitively is supposed to simplify and eliminate many possibilities that potentially are, but the principle will eliminate those and simplify the calculations, although they are complicated.
There is an inherent complexity to the Pauli exclusion principle that that grows as we add more and more identical particles. So, for instance, in the case where we have nitrogen atom and 7 electrons, we have 7 factorial, which is 5,040 terms that we have to calculate. So in the variational theorem, when I plug that 5,040 in, I'm going to have a sum over 5,040 terms. And so this matrix basically is a 3-dimensional matrix in the sense that we have a dimension over the basis functions k. So if we have 10,000 functions that we're using, we have a matrix that's 10,000 by 10,000. But then when we include the Pauli dimension, we have 10,000 by 10,000 by 5,040. And so the computation gets very difficult, very fast, so in factorial. So this is an NP-hard kind of problem. And depending on what kind of level you're at in terms of the complexity of this. So going back to this paper here. This one here, using the canonical ensemble, they were using 1,000 particles in their simulations, and they were averaging over using these auxiliary partition functions over all of the particles that they had in that particular system.
Okay.
Mm-hmm.
I have more, but maybe other people will ask and then I'll ask.
Maybe I say a quick thing. This is known in computational physics as the sign problem. So even the Monte Carlo approximations usually land on 0 when you have so many plus minus ones. The dimension just grows too quickly, which I think speaks to Keeper's point.
That's right, Clark. Thank you for that comment. Yes, so it's also known as the sign problem.
Okay, thanks. Yeah, do we have any more questions? Yeah, go on.
Can I ask a question?
Yes, sure.
My question is, I hope it's not too basic, but I thought with the, what's it called, the Pauli Exclusion Principle, it pushes apart electrons. So is that like, what's it, the electric force, which is mediated by virtual photons? What pushes apart the electrons? Is it virtual photons or it's something different?
What do you mean by pushes apart the electrons?
I thought there was repulsion between electrons with the Pauli Exclusion Principle.
Okay, so repulsion is a Coulombic interaction. Okay, so I don't have the Hamiltonian actually listed in any of the slides, which is too bad, but I can pull it up in a paper if I get to it. So the Hamiltonian operator is the sum of kinetic energy and potential energy. So the Coulombic term, so when we talk about the charge of particles, we're going to look at pair particle interactions in the Coulombic energy term. And when you have 2 electrons, you're looking at 2 electrons, you're going to have the charge -1 times -1, which is a positive sign, which becomes positive energy. Coulombic energy is generally a non-stable, so it's going to push those particles away, okay, from each other. And also we divide that term by the distance between the 2 particles, okay. And I actually talk about this, so this is a really interesting concept, being able to calculate the potential energy between nuclei and electrons, between all the nuclei, and between all of the electrons. So you have to go through that. In addition to calculating the Coulombic energy, you also have to apply the Pauli Exclusion Principle to that energy calculation. And so the same holds true with the kinetic energy. You have to go through the same kind of aspect with the kinetic energy. The kinetic energy term is 1/2 the mass of each particle. So you have to calculate the kinetic energy of each particle. But what makes our calculations different is that since we're not assuming the Born-Oppenheimer approximation, we also calculate what's called is mass polarization. So the mass polarization comes down to looking at pair particle kinetic energy and how a central particle or a central field and these 2 particles interacting, the kinetic energy as a 2-body problem going around this field is calculated. We call that mass polarization. So we include both of those.
Okay. Thank you very much.
Mm-hmm.
I have a question with regards to, sorry, can you hear me?
Yes, I can hear you.
Yeah.
Zoom caller. Don't know
Yes.
your name though. What's your name?
So, Sam.
Nice
Yeah.
to meet you.
So qubits are technically, I mean, we're still in the process developing, and you got trapped ions, you got, and okay, you could have a photon-based qubit. The qubits are in a wave sampling type of work that we are discussing here, a wave function, which is like a quantum annealer. We're not really, qubits are neither fermions nor bosons, but essentially we are mapping from, like a qubit to parafermions. Of course, when you say, oh, in a photonic quantum computer, a photon is essentially a boson because it's got a spin of 1. But hey, what are we discussing here in that sense? Why? So what I'm confused here is that qubits are being discussed in a wave function. What particle are we essentially talking about? Because qubit, if we are not talking about annealers, we are referring to a particular particle. So what particle are we talking about here?
Okay, that's a good question. In general, the qubit, the idea of the qubit is a general concept, and it hasn't been related to a single kind of particle. Let's see, where did I have that? Let me go back to that derivation. Okay, right here. So deriving the state of a qubit, we can get the definition of a qubit by assuming that the spin is 1/2. So we're assuming a 1/2 spin, but it has some kind of momentum behind it. So we typically denote momentum with L, with the L operation, L quantum number. And L is equal to 1 in this particular case. So we have an excited state. This goes back to the anti-symmetry property of the wave function. So it's usually a P or a dumbbell, right? A P state when we talk about chemistry. And this 1 can have a projection on the axis, the z-axis of either 0, 1, or -1. Just like spin can either be up or down, the angular momentum can be projected in either up or down, or not projected at all, which is the 0 state. And what's actually interesting when you go through this addition of momentum with spin, the state that actually has momentum in the down is 0. So that state doesn't actually exist. It collapses. So there's a collapse of the wave function for that state. And so you're left with only 2 parts in this particular addition of angular momentum, where the non-projected state exists, which is the 0 state of the qubit, and then the state where it's projected on the axis, which is the 1 state. Okay, and it does kind of get confusing here, because we usually think of 0 and 1 and up or down on Z, which is true because that is how the spin is actually being projected. The spin for the 0 angular momentum projection is actually spin up. Okay, so that's why even though the orbital angular momentum doesn't have any projection, it's being the spin is being projected up. So let me actually stop sharing my screen really quick at this point, and then go back to sharing a different screen. Stop sharing, and then let me pull up the graph block here. So here, share screen. I want to share this guy. All right. Okay. All right. So the 0 state is spin up. Generally, is how we think of that, right? Because that's what I was just saying, is that we have a 0 angular momentum projection, but the spin is projected in the up direction. Okay. And then for the 1 state, we have a positive angular momentum projection, which is this vector right here in the bottom, but it's down in the spin state. So the block sphere is really looking at spin, okay, the spin projection, and the projection of the orbital momentum on the bottom. So now if I operate with Z, it will flip the orbital momentum in some direction. But if I go back to the 0 state, there is no projection. If I operate Z, it doesn't do anything. Nope. Yeah. So if I go back to the one state here, let me refresh this really quick.
We could equally have a model here which is based on amplitudes. I mean, instead of and with spin as well. So a wave, has amplitude, lower and upper amplitude, and then again you can categorize as that. What does that amplitude signify? And I mean, there's the other part of this is that most people, from where the quantum computing technology is developing at the moment, people are looking at trapped ions or other bits and bobs. Trapped ion is one of them. You've got superconducting qubits and all that, and they are essentially looking at from a particle point of view, whereas this is a quantum wave annealer kind of thing, where you're looking at a Valley function, what sort of, and there I'm going with the amplitude. And, this is where the confusion kind of lies. What is a qubit here? Because to my mind, in the sense of wave mechanics, there is no clear-cut definition of what a qubit is. We can only, it's a mathematical function in a way.
If I can say one word, the qubits means that you have system which could have two separate states, yes. And for a quantum mechanical point of view, this is more natural. Put this kind of system to the spinor and for probably electron in the first place. And the second one, we use photon not because it's boson, but because you have two polarization, but these two polarization are effects of additional symmetry in this kind of particles. So the photon is also, you can describe photon by two different states, but you must remember that there is also another kind of symmetry, it's gauge symmetry, which reduce three states to these two states. So for me, definition of qubits is any system who could have two separate states.
But that's the thing, though. Qubit does not have two separate states. It is a superposition of states, which is where the wave mechanics kind of fits in.
Yeah, but and I don't say that it is. I say that it has two separate states. It means that if you measure this qubit, you have just one of two possibilities. Yes, because it's not the superposition is nothing has to do with this, because superposition is comes from quantum mechanical principle that you cannot, if you have a system which you could derive from in base from two different dimensions, you can take superposition of its, and this is also the states. So the main definitions is that you could reduce your system described by wave function or vector in Hilbert space to two-dimensional base, and this is what I mean by two different states.
Yes, and so in terms of a qubit with trapped ions, typically what we see is that when we use lasers to excite from one state to another, the laser is very tuned to excite to a very particular state, and that state is chosen to have the kinds of properties that we want to represent that qubit. And then, so if you want to go to a qubit where we have three states, which is a broader definition of a qubit, then you're going to have another laser that excites to that third state that's there. Or you can have many lasers that excite an atom to many different excitation levels, and that's the definition of a qubit, so multi-dimensional qubit.
Yeah, I mean, I get that. I think the major thing here is that which I obviously want to view. I think because now there are two levels of quantum computing is moving into two different spaces. You got D-wave type devices, which are waveform devices, which rely on quantum annealing, and then you've got gate-based devices, which are, which rely on particles. And I think probably this presentation is more suited to, would you say, to the D-wave type devices, where idea of qubit is more of a conceptual idea, it's a mathematical idea. But there is, because wave is, in a wave, how do you differentiate? I mean, just like we are just forming a mathematical basis of it. Is that a correct assumption here?
I would say that the method that I'm showing for chemical simulations is more appropriate to describe trapped ions than an annealer system. So we can use the methodology to say, okay, what does the calcium ion do in, whatever Google's doing? I know that they were building a device, I believe, if I remember correctly, with a trapped calcium. Cold quanta uses a trapped cesium. And that's also, they're looking at clock states, right? So we have a methodology for being able to describe what's happening to the actual atom on a very, very sophisticated level. And we can actually apply the gate operations that we do with lasers in those situations to that physical representation and actually model what's happening to the atom physically when we apply gate operations.
But you could do that same thing to any other element too. I mean, you can raise their excitation states, and you can, you really, whether by lasers or by magnetic field, you bring them up, you bring them down, So
That's
how is it different? Yeah. So how is it different then? There is no, it's, to me, because everything essentially on a quantum mechanical level is a wave. And I don't know what the state of trapped calcium is, but Microsoft, for example, was working on, I forgot now. My question is, how does one who's viewing this presentation from a quantum computing perspective, who do not have background in chemistry or physics, or even bare level maths, who are now engineers or people who are entering this field, they are very confused about, we've got this annealer device, and most people do not consider annealing devices as true quantum computing. I do, by the way, but that's a separate story. But then you have particle devices, gate-based devices, which are now being, being developed by these companies that are massive investment and all that. And then we are looking at this model here, which is kind of, to me, because it's wave-based, you're looking at excitation, because essentially it's either a electron cloud or things like that. You're looking at a wave. So I thought it's more towards the wave side, and this is where the distinction is not clear.
If I can, just one remarks. I cannot agree that wave function or states are wave. It is not true in classical meaning, because if it will be true, we will don't have quantum mechanics. You cannot say that states is wave in typical meaning, like wave in ocean or wave in light, classical electrodynamics light. It's not the same. You cannot reduce everything to the wave.
At a quantum mechanical level, again, Phoebe, I'd like to help us out here, and from whatever little knowledge I have, at a quantum mechanical level, light is a wave. No matter which light it is a wave. So I'm not sure what the thing is.
It's wave on some kinds of experiments, but on quantum mechanical level, it's not wave. It's a quantum system, which is more complicated than just wave. You can see light in some experiments, like they get some interference pattern like waves, but it doesn't mean that the quantum systems are waves.
Could you clarify what do you mean by state?
Yeah, you mean
you said that state is not a wave.
yes,
So
because
wave we understand, I believe. State is a little bit more elusive, has different meanings in different contexts.
Yeah, okay, but in at classical level, waves are described by realistic functions, and they describe something which could you take as realistic. In quantum mechanical levels, the states are some just information about your system, about your quantum system. So this is not the same to saying that, of course, you can change a vector in Hilbert space to the wave, but it is just bad name because it's conjugate with Schrödinger equation, which we call wave equation, but it isn't one-to-one like other wave equation. Yes, the objects the object in which you have in Schrödinger equation are not classical waves in this meaning. Yes, it's because you can find some experiments where you can measure not wave but particles. So it means that you have duality, but this duality means that your state is not something real, because we cannot take a real quantum system and say that this is state A or this is state B. You can just measure this state and reproduce just one of the vector in from base space. So this is hard because this is crucial information in quantum mechanics, that the objects in quantum mechanics are nor particles nor waves in classical meanings. Yes. So
yes, and I would also say that more broadly speaking, a state is how the quantum numbers that represent the system that you're looking at. So orbital angular momentum, spin momentum, and if you're talking about atoms, then you've got the principal quantum number. The state is what quantum numbers are and the values represent that state that you're looking at. So
yeah,
what are the yes.
Yes, sorry, but in classical physics, the states is everything about states you can say about if you have information about position and velocity. Yes, in quantum system you can say everything about your system if you just from spin numbers. Yes, because this is not the same to saying that you can reproduce everything. There are some, maybe this will be better. There are some numbers, quantum numbers, which are not connected with classical meanings. Especially is spin. Yes, you cannot say what classically mean spin, because there isn't exist anything classically which we could call spin.
And when you
yes,
say real,
yes.
when you say real, you mean in classical sense? Like when you say real, you only say
yes.
It's only in classical.
Yes,
right?
real is yes, because in classical theory you operate on the functions which are real and which you could reproduce from space on from space and from momentum. Yes.
So the imaginary, there are imaginary numbers and real numbers. So you say that the imaginary is only used in quantum to allows dealing with phases and stuff like that?
Yes and no, because even in classical electrodynamics, yes, because even in classical electrodynamics, you can use
Complex numbers. Yes.
complex numbers. It doesn't matter, but at level of states, it's a huge difference. Yes, if you use states from states derived from function or not from function. It came from commutation and non-computation of operators. Yes, because there are mathematical theorems which show you that you cannot if you have non-commutative operators, you could represent them only on the.
Phoebe, please could you take over, because I think we got only limited time. I
Yes.
would,
Okay.
Phoebe, that'd be great,
So
because I think we are getting distracted here a bit.
Okay, so the main information is that states are not wave. Okay, not classical object.
Thank you.
Okay.
Okay, good.
So really quick, I'd like to just make a quick announcement that if you want to learn more about these topics for chemistry, very specifically, we are getting ready to publish a book coming out in the summer of 2022. I hope I'm sharing my screen. It will be published by PACT, who also published Dancing with Qubits. The title of the book is called Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code. And I do have a co-author who's on the call today, Alon Chansey.
What level of knowledge do you require as a basic level to follow it through, just as a primer, or would you supplement it with some other material?
Yeah, so we're in the book, we plan to have a glossary of mathematical, or an appendix of mathematical operations. But in general, we're trying to write the book so that it's geared towards advanced high school students and early age college students who are not necessarily majoring in the topics, quantum chemistry or computing, but curious people, and or executives who might not have a background in the stuff. So we're trying to make it fun and exciting, where you don't have to necessarily have a background, but in general, the mathematics, the linear algebra, understanding, basic elements and periodic table is going to be something that we present in the first chapter of the book.
There's one last thing I wanted to, on your presentation, I wanted to get a little understanding of. You did mention deuterium, but I wanted your view on other noble gases, which also have matched pairs in a way. Can they be included in this? I know, because it's easier to work with hydrogen and deuterium because they're the first level. What about other noble gases?
Oh, yes. So we basically have calculated the elements up to nitrogen. So we've done nitrogen calculations. So if I actually go back to my references and pull up my Google Scholar page really quick and then share that window, you can go to my Google Scholar page. Let me see. Yeah, so we look at lithium. We look at small molecules like HD+. And then let's see if I can find my nitrogen paper is the highest element that we've actually looked at in terms of.
Will these be on the website later?
Yes, this is in the list of references, so I'm going to be giving them my presentation, and you should be able to have access to this. But all of these papers, typically on Google Scholar, you should be able to download. They might be offered And if you don't have access to any one of these papers on Google Scholar, then you can always email me and I can provide a copy of them as the author.
Thank you.
Awesome.
This is Ann Vroom talking. I wanted to ask you, Dr. Sharkey, if you could just spend a moment telling us a little bit about your business model. You know, what kind of compute resources you have, what kind of clients you have, and what service is it that you're offering?
Yes, so the idea is that we, well, first and foremost, it's a social enterprise. I'll go ahead and stop sharing it now. So Ode is a social enterprise, and attending events like this to educate the populace and writing the book is one aspect. So I have 3 departments in Ode. One is quantum education, being able to demystify quantum and make it more accessible for people to grow the industry. Then I also have quantum ethics department, so understanding how quantum is being used and for what purpose, and making sure that it's not being leveraged for malicious behavior and criminal activity. And then the other one is actual simulations. So being able to simulate very accurately using the methodology that I have shown you today, in a way that we can better understand chemical states and how we can actually leverage that to build more sophisticated devices, whether that is quantum computing devices, could be, whether that is used for space travel, jet propulsion, using very specific chemistry for jet propulsion. And so the idea is that over the summertime, I went through the I-Corps program, the National Science Foundation Innovation Corps, where I was able to, talk to many different potential customers. And I went from saying, okay, can I use this to model pharmaceutical needs, right? Chemistry of drugs. And what I found when I was talking to the pharmaceutical companies is the things that they cared about wasn't necessarily the things that I wanted to be able to address. So they cared about, sort of more optimization problems and being able to come up with very specific chemical properties, which is a very different kind of problem than the product I want to offer. So I, X'd out on the pharmaceutical design, although maybe one day I could probably get there. But I really narrowed this down to, okay, well, we have the ability to include a magnetic field and in the calculations. So yeah, we can actually model states of trapped ions. Okay, so that's one very particular aspect. And I can't talk about proprietary company information, but in general, the idea is that the product I'm developing called CLEAN, quantum learned electrons and nuclei, can be used to address very specific chemical problems. And one thing that I want to start to tackle is understanding trapped ions and maybe even jet propulsion and space travel, and using very specific chemical states in in plasma states. Computing resources. Right now, I just have my own computer that I'm using. For the book, we are using Google Colabs and actually using Qiskit in the book. So those are the computing resources that we have. I have been approved for Amazon Activate program, so that when I want to migrate my code from my personal computer over to Amazon and actually start using the resources there for larger and larger systems, I have been approved to use Amazon Activate program. And that is allows up to $100,000 in compute power, sponsored by Amazon, to answer your question.
That's wonderful. Congratulations on all of that.
Thank you.
Could you describe what you mean when you're saying a social enterprise? Is that an actual legal corporate entity type? Like I know there's certain social enterprise LLCs now, et cetera. I mean, what is it that you're signifying when you use that term?
Yes, so I actually have started what is called an L3C. And L3C stands for Low Profit Limited Liability Corporation. And that basically has to do with a tax standing that's not recognized in every state. It's recognized in about 10, and Wyoming happens to be the state that I formed my entity in. But what that has to do with is that 5% of the profits that we have in the organization has to go back towards an education specific effort, and typically nonprofit. So 5% of my revenue needs to go back towards the education. And that's what is meant by social. So being able to benefit the society in some way where we have some sort of foundational goals, right? And so for me, that's quantum education. For Ode, we are, focused on quantum education. Now, right now I'm giving back mostly in being able to dedicate time to presentations and attending conferences and, speaking with students and writing books and things like that.
Wonderful. Thank you. And again, congratulations.
Thank you. I appreciate that.
Okay, Kibor, you show us the two kinds of methods with approximation of quantum states of chemistry atoms. Could you say in your methodology, could we find some points where the Born approximation not works? And because you use some kinds of approximation, and with second methodology was without this approximation, if I understand. And the second question is because you compute a lot of coefficients, how to call it doesn't matter, but could you use some methods connected with Feynman diagrams? Because in quantum field theory we compute 1,000 of these similar coefficients.
Yeah, so I don't use Feynman diagrams at all in the work that I've done, but I foresee that I could possibly do that. In terms of Born-Oppenheimer approximation, what happens is that the Hamiltonian that we use to measure the energy is significantly reduced when it comes to the kinds of things that we look at. So typically in the Born-Oppenheimer approximation, we only consider the motions of electrons, and we basically think that the nuclei are static point particles that don't really move. And then we have to go through, this idea of quantum Monte Carlo was brought up on the phone. Clark mentioned it, where we have to basically look at the random generation of how nuclei move around, but they're still point particles. And so this comes back to the Heisenberg uncertainty principle. So the more you know exactly where a particle is, the less you know about its momentum. So the Born-Oppenheimer approximation really breaks down in the sense that if we know exactly where a nuclei is, we have no idea any information about the momentum that it obtains. And in general, electrons are dominated by the motions of the nuclei. So if we're violating the uncertainty principle by assuming that they're point particles and that we know exactly where they are, you can imagine that we have very confused electrons. Now, it's in general a pretty good approximation when you're looking at only ground states. So when you're looking at the lowest possible energy of a system, you can basically assume that the nuclei are more or less not being excited, and they're not, moving around, and that they don't really have momentum very much. But as you excite a system and the nuclei become vibrationally excited or rotationally excited, then the electrons are going to follow those motions of the nuclei. And if you're still assuming that they're point particles, then you're violating the Heisenberg uncertainty principle. You're not going to get a very good representation of the energy associated with those electrons. And further, the Born-Oppenheimer approximation doesn't allow you to calculate mass polarization. So polarizing effects, in other words, how do waves interfere with one another? Or how do they, so you have, positive interference and negative interference, where the wave functions collapse. And so the Born-Oppenheimer approximation doesn't allow you to look at this interference between the masses and the charges.
Yeah, great. Because as we know, physics is magic or philosophy of approximation.
That's right.
Good. Thanks, Kieper. There's a question about materials. Helen, I'm not sure if you are with us, but I know that usually you also post the materials on the events website. Do you think that it will be the same this time?
I'll do it in email.
Oh, by email. Okay. So if someone is interested, yes, please post your email on the chat, and then Helen will send the slides. All right. I don't see more questions now, so I think, Helen, I think that we can now stop recording. And yeah, Kieper, thank you once again for a great talk and also participating in the discussion, answering all the questions. So I think that the discussion was also very interesting. So it took more or less the same time as the lecture. So it implies that, it was very fascinating for our participants.
Yes, thank you for having me. Yes, thank you.
Great. We would also like to thank all the participants for attending this event. And yes, that's the last meeting, that's the last meetup before the Christmas and the next year. And we would like to wish you Merry Christmas and happy 2022nd year. And we hope to see you again in January.
I just want to thank you everybody and thanks the presenter, and I hope you'll come back again in future. So have a great holidays. Okay, thank you all.
Thank you.
Thank you. Bye bye. Thanks, Phoebe.